So in this video we are looking at introduction to combined cycle processes, and we'll start with a little bit of general theory about combined cycles, what's the basic idea behind it, and then look very briefly into the beginnings of how we combine specifically gas turbines and steam power plants. So to begin with, the general principle of combined cycles, we'll start with the two-temperature heat engine that we had at the end of very first lecture of the whole course. So definition of efficiency for a two-temperature heat engine, where you take heat from a heat reservoir at temperature T hot, you take the amount of heat QA, and we can, with two-temperature heat engine, we can produce some amount W of work, and the rest of the heat we reject back to the environment. So the efficiency is then defined as this amount of work that we do divided by the amount of heat QA. Or alternatively, we can represent the work as the difference of these two heat flows. So according to first law of thermodynamics, we cannot create or destroy energy. So in stationary state, that means that this amount of work here has to be what is the difference between these two heats. And then we can divide with QA, and we get 1 minus this heat rejected divided by the heat input. Now with combined cycle, the idea is that if we have a process that is working at fairly high temperature, then possibly the heat rejection temperature is also fairly high, and we can still use that amount of heat that we would otherwise be rejecting. So we start from the same two-temperature heat engine, but we consider this now to be the so-called topping cycle. So very same definition of efficiency, but we now just differentiate this work as W1 because we are getting another work done as well. We use this QB as input to our bottoming cycle. Okay, we might not be able to recover all of the heat, so this QC that goes actually into the lower temperature two-temperature heat engine is only what is left remaining after we've lost some bit of heat, which we probably usually will be losing. And then from the QC we generate some other amount of work, W2, and a smaller amount of energy is lost to the cold reservoir. So bottoming cycle efficiency definition is the exact same. We can define it either way, either as the ratio of work to heat input or 1 minus rejected heat divided by heat input. With these definitions we can combine for the combined cycle efficiency. We're still inputting only the QA, but we're now getting two works out, or alternatively 1 minus the combination of these two losses, so heat rejected by the low temperature process plus the Q loss that we lost in trying to recover the heat into the low temperature heat engine. And because the amount of heat taken by the topping cycle is clearly going to be greater than the amount of heat taken by the low temperature heat source, what this means is that the efficiency of the topping cycle is always going to dominate the total efficiency, but as long as we can squeeze in a low temperature heat engine here at the bottom, we are always going to improve our efficiency. So this is the general principle of why a combined cycle would be a good idea if we can manage to make a lower temperature process work with the rejected heat of the high temperature process. So when might this be possible? So we have different types of heat engine processes with different temperature levels. Diesels, gas turbines, fuel cells. Okay, fuel cells are not exactly common at this point, kind of up and coming technology. Then we have low temperature processes like the steam process that we have been dealing with, and ORC, which is the lowest temperature of our processes. So typically when we talk about combined cycle power plants, unless we specify something else, we are usually meaning gas turbine topping cycle and steam turbine bottoming cycle. So this is a very, very common technology throughout the world. Lots of power plants in various countries. In Finland, maybe not so many, so we have a few, but the problem is that already before the recent energy crisis, the prices of natural gas and light oil were so high that it was not really very profitable way of producing power. But in countries where gas or oil are cheap, this is a way of generating very high efficiency power generation power plants. And the other cycle that is somewhat less used but can be somewhat relevant is when you have ORC, organic Rankine cycle. So kind of like steam cycle based on Rankine cycle, but using some organic fluids like toluene, for example, instead of water. This way we can get the plant to work at lower temperature levels, lower pressure levels, and we can get by with slightly lower temperature heat inputs, and these kinds of concepts have been proposed and are in some amount of use, not very common, not very large, but they are being used operationally to produce some additional power from, for example, reciprocating engine exhaust or other kind of moderate temperature heat sources. Now if we look at how in this our specific case of gas turbine and steam cycle, what kind of Carnot efficiency, so Carnot efficiency, as we remember, that is the highest theoretically possible efficiency we can get when our heat input, average heat input temperature and the average heat rejection temperature are given. So theoretically, if we have either gas turbine, very high temperature of heat input, but also fairly high temperature of heat rejection, or conventional steam cycle, lower heat input, but also very, very low temperature of heat rejection, we get around 50% Carnot efficiencies, clearly less than that in real power plant, but this is the theoretical maximum allowable with these temperature levels according to the second law. Now, if we add reheat, for example, we can get some amount of increase for our steam cycle, but not really that huge. But if we are able to combine the high heat input temperature of a gas turbine with the low heat rejection temperature of a steam cycle, then we're able to make a quite dramatic increase in our theoretically available efficiency. And again, in reality, it's going to be less than that, but still clearly greater than either steam cycle power plant or gas turbine power plant by themselves. So how it look like in practice is something like this. The simplest possible way, if we have just the de-aerator, condenser, pump and turbine for the steam cycle, gas turbine works here just as a conventional open simple cycle gas turbine. Exhaust gases are sent to the heat recovery steam generator, and then we have the economizer, steam generator and superheater to produce steam for the turbine. And this process neatly fits below the gas turbine, so we can transfer heat from the exhaust to this cycle, and basically without putting any more fuel in, so only fuel input, only fuel consumption and only heat input is here in the gas turbine combustion chamber, and everything produced by the steam cycle is basically a free bonus as far as energy consumption is considered.